Welcome to Geometry Unit 4, Section 1, Bisectors of Triangles. How come there aren't any trisectors of biangles? Ba-dum.
Kinda grabs you by the boo-boo, don't it?
All right, so perpendicular bisectors. In Lesson 1-3, we learned that in any segment line or plane that intersects a segment at its midpoint is called a segment bisector. So when we see a diagram like this, where this segment AB has been cut into two equal pieces, we would say that line PQ bisects segment AB.
Wow, man.
Yeah. Um, a perpendicular bisector now is a perpendicular segment, right? Or it's anything that is perpendicular to the segment that's being bisected. That's called a perpendicular bisector. So in this drawing, this diagram here, we would say that line RS is the perpendicular bisector of segment JK.
Hey! What are you trying to do?
Well, I'm trying to teach geometry. Perpendicular bisector theorem says this: if a point is on the perpendicular bisector of a segment, then it is equidistant from the endpoints of the segment. So what does that mean? Well, let's take a look at this diagram here. So we have is segment AB is perpendicularly bisected by line CD, right? It says here at the bottom, line CD is a perpendicular bisector of segment AB. Well, if that's true, then what we have here are two congruent segments, okay? And basically how we can prove that, we would say that, well, because of perpendicular bisector theorem, or the definition of a perpendicular bisector, segment AD is congruent to segment BC, right? So we would make that statement. Right, by definition of perpendicular bisector. And we could say that segment CD is congruent to segment CD, and that's just reflexive property. And then we could also say is that angle CDB and angle CDA are right angles. And that's because of the definition of perpendicular, right? We make right angles. And we could then say that angle CDB is congruent to angle CDA. And why would that be? Because all right angles are congruent. They're all 90 degrees. And then we could finish up by saying that triangle ADC is congruent to triangle BDC, and it's by side angle side. And the last thing we would say is segment AC is equal to segment BC, and that's because the corresponding parts of congruent triangles are congruent. So that's a proof that we just did. So I just proved the theorem. The thing I need you to be able to do is to use it.
Hey, hang on, you guys. I'll be right back.
Okay, so if a point is equidistant from the endpoints of a segment, then it is on the perpendicular bisector of the segment. Well, we can go through the proof of all this very quickly by basically saying, well, these two triangles then are congruent by side, side, side. Okay, so I would say triangle ADE is congruent to triangle BDE, and that's through side, side, side. And then what this would say is we can see that this is that goes through this midpoint, but how do we know it's a perpendicular bisector? Well, we would say that angle BDE and is congruent to angle ADE, and that's by corresponding parts of congruent triangles are congruent. So now, because they're congruent, we would also say, if we say angle BDE and angle ADE are a linear pair, and that comes to us from the diagram. We could look at the diagram and say that's what they are. And since they both are a linear pair, and therefore they are right angles. Right? And that's due to both angles would have to add up to 90, since they're right angles angles that are congruent that form a linear pair of right angles, right? And last thing we would say and then is that segment AB is the perpendicular bisector of segment CE. Okay? So we've gone through the theory, the converse, and proved both. So use them. That's what we're going to look to do on the worksheet that you'll be given.
This sounds so real funny, man. Me and your mama.
All right, when three or more lines intersect at a common point, then those lines are called concurrent lines. Okay, three or more. Okay, so they all meet at the same point. So we could look at line L, line M, and line N. They are concurrent at P, point P.
Hey, who cuts your hair?
All right, so since these lines meet at point P, then point P has a special designation. That is the point of concurrency.
What's the hassle, man?
All right, so the circumcenter of a triangle. Okay, since a triangle has three sides, so it's only logical it has three perpendicular bisectors.
Hey!
These perpendicular bisectors are also concurrent lines. They all meet in the same point.
Okay, man, start it up.
So that point of concurrency of a perpendicular bisectors is called the circumcenter of the triangle.
Fire it up, Holmes.
Okay, so the circumcenter is the same distance, all right, from each of the vertices of a triangle. So if O is the circumcenter of triangle ABC, then AO equals BO equals CO. So this point here, all right here, this point, is the same distance from point A, from point B, and from point C. Now, the interesting thing about this is dependent upon the type of triangle you're looking at, where the circumcenter is going to be. On an acute triangle, it's going to be inside of the triangle. On a right triangle, it's going to be at the midpoint of the hypotenuse. Okay, so here we are inside the triangle. This is at the midpoint of the hypotenuse. And the obtuse triangle, it's going to be outside of the triangle. What this creates, each one of these situations, is a circle. That the center of that circle touches, is where that located is, but that circle touches each of these vertices. All right, so it would go around. All right, I'm going to draw a circle here the best I can. So this circle, the radii of the circle go to the vertex. Okay, an angle bisector is it could be a ray, it could be a line, it could be a segment, divides an angle into two congruent angles. So we would have these two angles here be congruent. All right, it can be a line, a segment, or a ray, as we stated.
Young man, now give me that knife. Thank you.
All right, so the formal definition is the locus of the points in the interior of the angle equidistant from the sides of an angle. So ray BD is the angle bisector of angle ABC in this picture.
Hey, this is great, man.
Okay, so our drawing's off a little bit on this, but we're going to, go through the proof anyway because it still works. So if we are on an angle bisector, so we are given this information, right? This is perpendicular here, and this is perpendicular. Those are congruent angles, right? So that would mean these are right angles also. So what we would say is because this angle is congruent to this angle, and this angle is congruent to this angle, and we have a common side with this situation. So this segment is congruent to itself. We would then be able to say that triangle DFB is congruent to triangle DEB. And that's because we have angle, side, if you remember from the last unit. So because those two triangles are congruent, we would say that segment DF is congruent to segment ED, right? And that's through corresponding parts of congruent triangles are congruent. So we have that figured out, so we have to be able to use this again.
Hey, this is great, man.
Okay, if a point in the interior of an angle is equidistant from the sides of the angle, then it's on the angle bisector. So all we're doing is working this in reverse. We're saying we've got this right angle, we've got this angle here, segment congruent to this one here, right? So what we would use is hypotenuse leg, because we have the same segment, right, sharing here. So if it's a right triangle, we use hypotenuse leg, which is a different theorem. We have not talked about that yet. We will when we get to right triangles. So We would then say the two triangles are congruent. Well, then that says that this angle is congruent to this angle by CPCTC. So basically, it's the knowledge I need you to do, not the proof. So if they're perpendicular to the ray and they're equidistant, then angle BD bisects angle ABC. Okay, so similar to what would, excuse me, the incenter of a triangle. Similar to perpendicular bisectors, since a triangle has three angles, it also has three angle bisectors.
Hey! What are you trying to do? You ruined my record, man. I just bought it.
All right, well, we'll do what we can to fix that. The angle bisectors of a triangle are concurrent, and their point of concurrency is called the incenter of a triangle.
Bye-bye, lardass.
Okay, so what happens is with the incenter of a triangle, I have a circle. And since the radii of a circle are all congruent, then that's going to be the equidistance. Okay, so we're not going to go through the proof of this because it is very long and very drawn out. But we're just going to apply this and say when we have an incenter, we have a circle that is inscribed inside of the triangle in center, right? And then the center of that circle makes all those radii congruent. Okay.